Welcome to the chapter on practical applications and core concepts of alternating current. In this chapter, we'll explore how AC is integral to household appliances and power transmission. We will introduce fundamental concepts of AC theory, including the nature of alternating current, the role of transformers, and key parameters like frequency and phase difference. These insights will help you understand the importance of AC in everyday life and its underlying principles. Alternating current, or AC, is a type of electrical current where the flow of electric charge reverses direction periodically. This is in contrast to direct current, or DC, which flows in a single direction. AC is typically represented as a sine wave, with the current changing direction and magnitude over time. The production of AC is primarily achieved through electromagnetic induction, a process where a changing magnetic field induces an electric current in a conductor. This is most commonly done using generators. In a generator, a coil of wire is rotated within a magnetic field, inducing a voltage that drives the alternating current through the circuit. Large-scale production of AC occurs in power plants, where mechanical energy, often from turbines driven by steam, water, wind, or gas, is converted into electrical energy by rotating generators. The generated AC is then transmitted through the power grid and distributed to homes and businesses for everyday use. In AC circuits, components such as resistors, capacitors, and inductors behave differently compared to DC circuits. In resistors, the voltage and current are in phase. In capacitors, the current leads the voltage by 90 degrees. In inductors, the voltage leads the current by 90 degrees. In AC circuits, power can be classified into three types. Active power, denoted as P, is the real power consumed by the circuit and is measured in watts. Reactive power, denoted as Q, is the power stored and released by inductors and capacitors and is measured in volt-amperes reactive. Apparent power, denoted as S, is the combination of active and reactive power and is measured in volt-amperes. The relationship between these powers is given by the formula S equals the square root of P squared plus Q squared. An electromagnetic oscillating circuit, or LC circuit, consists of an inductor, denoted as L, and a capacitor, denoted as C, connected together. It can oscillate at its natural resonant frequency, given by the formula F0 equals 1 over 2 pi times the square root of LC, where F0 is the resonant frequency in hertz. Electromagnetic radiation is the propagation of electromagnetic waves through space. These waves are generated by the acceleration of charged particles and include radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The speed of electromagnetic waves in a vacuum is the speed of light, approximately 3 times 10 to the power of 8 meters per second. The relationship between the speed of light, frequency, and wavelength is given by the formula C equals F lambda, where C is the speed of light, F is the frequency of the wave, and lambda is the wavelength. Let's examine the behavior of LEDs when powered by an alternating current. Since LEDs require direct current, the AC must be rectified. This process introduces a brief switch-on delay as the current is converted and filtered. You might also notice a slight ripple in the brightness of the LED due to the incomplete smoothing of the AC to DC conversion. Induction cooking is a practical application of alternating current, where AC induces a magnetic field in the base of a cooking pot. This magnetic field generates eddy currents, heating the pot directly. The efficiency of induction cooking is notably high because the heat is generated directly in the pot with minimal energy loss. Wireless charging is another practical example where AC plays a crucial role. Inductive charging relies on alternating current to create a magnetic field, which then transfers energy to a receiver coil in the device. The efficiency of wireless charging depends on the alignment and distance between the charging coil and the device's coil. Transformer-based power supplies are essential in everyday electronics. Step-down transformers reduce the high-voltage AC to a lower voltage suitable for devices like laptops and phones. The AC is then rectified to DC, which these devices require. Additionally, transformers provide electrical isolation, enhancing safety by separating the high-voltage and low-voltage circuits. This concludes our chapter on practical examples and AC theory. Understanding these principles is fundamental for electrical engineering students as they form the basis for more advanced topics in the field. Thank you for watching.